Okay, so for this chapter, okay, I just continue lah. Okay, sorry, ambil masa yang lama kan, ada masalah sikit. Um, Kalau tengok dekat sini, okay, for this chapter actually we mostly deal with the condition that high pressure, high temperature lah. And in order to get the volume, so we're gonna measuring the fluid, macam fluid untuk for the sizings of the reactor, right? Piping and distillation column and so on lah for other unit of operations. Okay, because generally the gas is not obey the ideal gas law. Okay, uh, and kalau kita consider kan, from the range of the intermediate to high pressure, right? Selalunya molecules is close enough, okay, and then there is how to say that the intermolecular interactions is occur between the molecules, okay. That's why if we consider the why we consider the compressibility factor, okay, for the calculations, actually the value of the compressibility factor is deviate from value of 1. Okay. Awak mesti ingat kan the ideal gas law. PV equal to ZRT but Z is equal to 1. Okay. Actually there's a special range for when we considering the ideal gas equation for the calculation of volume, pressure and also temperature. Okay. Later I will show you the range. Actually is just around 0.98 to 1.02, I think. Okay, if I'm not mistaken. Okay, so we're gonna deal with the pure fluids. Okay, pure fluid is just like a methane, ethane, just one component. Okay, whether in liquid phase or vapor phase. Mostly we deal vapor and liquid lah. Okay, not for the solid. Okay, so dekat sini kita akan tengok lah. Okay, uh, dia punya the equation that you can use for the calculation all the thermodynamic properties lah. Okay, tapi kita akan deal juga dengan ideal gas equation. Okay, uh, okay, so for the topics of uh, this chapter actually introduction about the volumetric properties. Okay, PVT diagram, PT or VT diagrams. Okay, where is the single phase or two phases, 3 points, and also 3 points tu macam dia punya ni lah, gas, vapor and liquid exist at the same time, right? And then volumetric properties of the equation of state. Okay, kalau tengok dekat sini, mana annotated? Okay, ideal gas, virials and general equation. So this is what we call it as equation of state, EOS lah. Okay, and then volumetrics for generalized correlations, gas and liquid, vapor. Yang ni kita akan guna table sebab tu the main textbook is important because you need to do the interpolation or extrapolation to determine the for example like enthalpy, entropy kan. For vapor, liquid, volumetric generalized correlation. Okay, kenapa saya punya tengok. Okay, so kalau untuk generalized correlation, for this part we will use to calculate the virial as well as compressibility factor lah. Okay, because kalau awak pernah ingat, you guna untuk calculate compressibility factor, you have to determine total Z is equal to, siapa ada ingat? Saya pun tak ingat. Total Z equal to Z prime plus Z not plus Z prime lah, omega Z prime. Okay, yang tu baru you akan dapat total Z. Okay, okay. And then volumetric properties from the thermodynamics tables and diagrams, but not all the component that we can use for the tables and diagrams. Okay, that's why we need this equation, like a virials and also generic cubic equation. And for generic cubic equation, actually we can divide it into radicon, soft radicon, as well as Penrobiston, okay, and vapor liquid equations lah. But we still need information from the radicon, soft radicon. Yeah. Okay, so just introduction about the volumetric properties. Okay, I think this is the topic that we're going to cover lah. Okay, for if possible, we will deal with the cubic equation of state lah. But at first, I will explain about the equation, ideal gas state equation, and as well as apa virial equation. Okay, how to use virial equation. Okay, there's a two condition that you can use for the virial equation, and the range of pressure that you can use for the virial equation lah. Okay, so for the vapor, I think you are familiar with this. What is it? What we call it as a PT diagram of your substance, right? I think this one is the diagram is for water. Okay, but the trend is similar with the other components. Okay, whether it's methane, ethane also. So if you look at here, and we have a solid region here. Okay, we have a solid region. We have solid region on the left side. And then, so we have a liquid region here, you have to remember, and this one is vapor. Okay, and we have a triple points. So I think all of you know how the degree of freedoms. Okay, this one is degree of freedom. This is a what we call it a vapor and liquid exist together lah. Okay, this one is a liquid and solid. Okay, this is sublimation curve. This one is evaporation curve lah. Okay, this one is a fusion curve. Okay, and C is the what we call it as apa critical point. Okay, so this is supercritical T over TC. Okay, the vapor behave like a liquid. Okay, this is what we call it as supercritical lah. Okay, it's stay as a vapor or gas, but it just behave like a liquid lah. Okay. Apa lagi? Degree of freedom, right? Okay, I think all of you know how to calculate the degree of freedoms lah. Meaning that if in the single phase, what is the degree of freedoms? Meaning that kalau you nak stay dekat liquid region, okay, ataupun dekat vapor region, okay, berapa variable yang you boleh ubah? Okay, contohnya kalau phase dia adalah satu, okay, number of species satu, okay, 2 minus 1, 1 plus 2 is a 2. Meaning that temperature and pressure we can vary. Okay, to stay in the liquid region, only in liquid region. But if you want to stay in the, how to say, kalau nak maintain dekat vapor and liquid, kan, dekat garisan ni, okay, dekat the ni panggil apa? Evaporation curve, kan? So you boleh maintain satu variable, whether temperature or pressure lah. Okay, tapi kalau kat sini you tak boleh ubah apa-apa lah. Okay, degree of freedom dia kosong. Yang ni dua kan. Yang ni satu. Okay, faham eh? Okay, so this is another angle for the PVT diagram lah. So we call it a PV diagram for pure substance. Okay, so in PV diagram, the phase boundary becomes area or region. Okay, kalau you tengok kat sini, nampak ni. Why we call it as a PV phase boundary become area or region? Because this one ni, nampak ni, liquid and vapor. Okay, this is a triple point. Okay, and this one is a solid and as well as liquid. And critical point here. Okay, so this is the how it changes from the liquid to the gas lah, ataupun daripada vapor ke liquid kan. So this is the vapor and liquid exist together lah. Okay, okay, faham Ada nampak So yang ni single phase, yang ni adalah single phase untuk vapor, yang ni ada single phase untuk liquid. Okay, so all this one is the critical ten. Kalau nampak dekat sini sebenarnya yang ni lah kan, T over TC, yang ni TC kan, sebab ni adalah line untuk critical point. Okay, this one T below than TC, sebab sini adalah TC kan. Okay, yang ni more than TC lah. Okay, okay, so this is if you look at 3 dimension lah, from PV and T. Okay, so if you look at, generally we see from this side, right? Okay, kita tengok daripada ni PT diagram kan. Yang awak nampak tu dia punya, nampak mana? Ni lah. Betul lah PT diagram kan. You nampak daripada sini kan. Nampak garisan ni and nampak yang garisan ni kan. AAA. So you akan nampak yang tadi tu PT diagram dia adalah macam ni lah kan. You tengok daripada sini. Kalau PV you tengok daripada sini lah. Okay. Kalau you tengok daripada sini adalah VT diagram. Okay. Faham eh? Okay. Okay. So apa ni? Kalau kita tengok kat sini, okay. Fluid can be a liquid, gas also liquid and gas lah. Dia punya equation ni lain ya. Kalau untuk liquid, kalau you nak calculate dia punya volume pun dia ada special equation dia. Okay. Memang you boleh guna equation untuk daripada gas, tapi dia tak akan accurate. Okay, it's possible to see to use as a approximation lah. Okay, but we have a special. Similarly, also if you want to calculate the information of the value of the like a volume at the two phase system, right? Liquid and gas. Okay, like a heat. Okay, so kat situ kita kena guna equation yang liquid juga. Sebab dia punya bila dia dalam two phases, dia punya komponen tu ada yang dekat liquid dan juga ada yang dekat gas. Okay. So generally, okay, if the system is at any temperature or pressure, T more than Tc, of course, is going to be gas. Okay, definitely. But if the condition, kalau you nampak condition tu adalah T below than Tc and P more than Pc is going to be liquid. You just refer. Before you start any calculation to determine the PV or T, tengok dia punya condition dulu. Okay, for the pure substance. Whether you punya substance adalah dalam liquid ataupun gas. Okay, ini important when you want to do calculation for the cubic equation of state lah. As well as generalized correlation. Okay, virial, saya rasa virial juga. Okay, this is important to know the condition of your system, whether liquid, gas or two-phase system. Okay, yang tu kita panggil saturated lah. So generally ini you punya starting. Sama ada you tengok sama ada you akan tengok daripada table ni ataupun you predict daripada PT diagram tadi lah. Okay, PT diagram ni. Apa-apa you kena tahu you punya phase. Okay, whether is it in vapor or liquid generally. Okay, kalau kat sini bila guna liquid, you kena guna liquid equation lah. If vapor, you kena guna vapor equation lah. Okay, this is especially for vapor and liquid equation lah. From the cubic equation of state. Okay, that is important. Okay, tapi guna table ni pun you boleh guna. Okay, faham eh? So kalau dekat sini, kalau T below than Tc and P below than Tc is going to be gas lah. Okay. And then we have to see the boiling point first for the T. Okay. Whether it's a gas or not. Okay. If more than boiling point or TBC, okay, maksudnya dia gas lah. Okay. Tapi kalau lower than TBT is going to be liquid lah. Okay. Sebab kalau you ingat dia boleh you boleh bawa ke sini ke sana kan. Okay, different temperature and different pressure lah. Okay, and T below than Tc, P below than Tc is gonna be two phase liquid if the temperature is similar with the T boiling point. Okay, faham ya? This is information only for H2O T34 and PC is 220 bar lah. Okay, so you kena ingat. Okay, how to determine the pure phase, the phase for the pure substance? First, actually, we can use the Antoine equation. I think all of you know. Okay, even we're gonna use this Antoine equations for these courses. Okay, and if you have a main textbooks, we're gonna refer of in appendix B1, I think. So let me check. I'm not sure. Antoine equation. All the information I think is from the yeah, table C1, C2. Okay. And the properties of the pure substance you can refer to the table B1. Okay. So this is the Antoine equation. Actually, we have another equation similar like Antoine equation. We can use for the broad range of the temperature. Okay, we call it apa? It start with the W. Wagner, I think. So Wagner equation. Okay. We have to use that one because entering equation is for the, I think for the new edition of the book, they stated the range of the temperature that you can use for the entering equation. Okay, but for the very old, like the first edition, three editions, they never stated the range of the temperature that you can use for the entering equation. Okay, so for the broad range, I think we can use for by using the Wagner equation lah. Okay. I think we're going to cover in chapter 6 or chapter, I don't remember. Okay. But I think I still remember is I think is a Wagner equation. Okay, for the broad range. But for the studying, you can use this Atherton equation. And then yeah, volume actually for liquid is not depending on the pressure and temperature, but gas, yes, is going to be dependent and depend on the temperature. Actually, it's depend on pressure and temperature for liquid, but it's the changes is very small. Okay. Um, we can see clearly only for the gas lah, sebab dia akan effect, sebab bila you increasekan temperature, dia punya molecule interaction and repulsion is gonna be increase the intermolecular interaction, sebab tu dia akan effect you punya pressure and also you punya volume lah. Okay, so the mathematical relation that we gonna use for the calculation of PBT is called equation of state lah, including ideal gas equation as well, virial as well as cubic equation of state and generalized correlation. Okay, so for the single phase regions, for the PV diagram, single phase equation. Okay, so this is as a function of pressure, vapor and temperature. For now, we focusing on the, I think it's just a vapor pressure and temperature. Okay, I think so lah. Yes, PVT lah. PV equal to ZRT lah. Okay, so the simplest equation of state yang you dah belajar, actually is a equation of state. Okay, we consider as a Z equal to 1 lah. This one is very low pressure lah, valid for low pressure. Why we, okay, why we use at the low pressure? Anyone? Not at high pressure? Siapa? Kenapa? Kenapa kita consider kita boleh guna dekat low pressure tu? Yelah, ideal gas at low pressure lah. Why? Kenapa kita tak guna dekat high pressure? Ahmad Arif. Semua dah masuk UTM ke? Kalau high pressure bukan ideal. Yelah, kenapa lah? Memanglah bukan ideal. Awak ni benda yang sama juga kan. What is the assumption when you want to use this ideal gas equation? Saya? Kenapa? Kan nak malah Arif. Memanglah high pressure bukan ideal lagi pressure. Semua dah ada buku ke? Dah order dah? Semua dah ada buku tak? Baru order, okay. Ya, sampailah. Kenapa Arif? Nak malah Arif? Master Mass Balance ada info tak? What is the factor, the reason lah, assumption dia. Salah satu assumption je lah. Apa dia tadi? You can unmute lah if you want to say. Tak tahu. Ha? Tak pasti. Yalah, masa bila? Memanglah. Low pressure, how low your pressure actually? How low? Okay. How low your pressure kalau you nak use. Kan? Okay. Dia salah satu dia intermolecular interaction lah. Okay. Kita boleh consider ada tu ada tapi dia terlalu kecil lah. Dia akan static macam tu je lah. Tapi bila high pressure intermolecular interaction kan dia orang panggil apa? Dia bergerak kan. Bila high pressure ataupun high temperature kan. So dia akan close each other lah. So bila high pressure, repulsion dengan attraction tu ada. Sebab tu kalau equation of, kalau you perasan you belajar dekat mass balance, You belajar van der Waals kan. That is kita consider equation of state lah, cubic equation of state. Kalau tak silap saya, yang equation yang ada A, yang A sebelah kiri tu, yang you tambah dengan B tu kan. Okay, dia yang first tu adalah, kalau tak silap saya, repulsion, yang second tu attraction. Okay, saya lupa. Okay, tapi dia ada attraction dengan repulsion. Okay, sebab tu kita consider attraction. Sebab kalau kita you calculate Z, okay, kalau you tengok mana-mana pun buku kan, okay, dia akan perasan kalau ini adalah value 1 kan, Z versus, sekejap, Z versus apa? Pressure saya tak ingat lah. Sekejap, saya check. Pressure, saya rasa pressure. Saya rasa pressure. Okay. Ataupun temperature lah. Dia akan, dia macam ni kan, dia akan deviate. Dia akan deviate. Kalau ni pressure lah, kita boleh consider dekat sini je. Kan? Tapi lepas ni, dekat sini adalah attraction kan. Sini ada repulsion. Kita boleh, alamak, hilang pula. Okay. Sikit je. Yang you consider tu sebenarnya dekat sini je. Tapi bila dah high pressure, kat sini kan, kita dah tak boleh lah. Kita nak consider dia punya, kena consider dia punya, sebenarnya ni dah masuk lah nanti. Ini just sketching kan. Dia dah masuk repulsion dengan attraction lah. Okay. Z tu satu kat sini. Sebab tu bila you consider kan, kalau you zoom kat sini, sebenarnya kalau you zoom dia nampak dekat dengan satu lah. Tapi bila you tengok secara overall the figure, dia akan dapat macam ni lah. Saya rasa dekat buku ada. You boleh tengok dia. Saya tak ingat. Sekejap saya check. Nanti kita akan guna masa bila awak guna virial, masa bila awak guna cubic equation of state. Tu ada. Saya rasa figure, saya tak tahu figure, kalau buku lama 3.10 lah. Okey. Tapi kalau figure, kalau buku baru saya rasa 3.11. Tu ada Z versus pressure lah. Z, the compressibility versus pressure lah for the virial. Okay. Okay. This one is for the, I think is for the liquid. Okay. Actually, for the liquid inclusive fluid, we need the what is it? Beta and K lah. Okay. This one is for the incompressibility liquid lah. Okay. I think for this one, I think we gonna focus on the ideal and also for the high pressure. Okay, so as the comparison for the other gas, Z is equal to 1, valid at low pressure. Right? And equation of state, from the PVT data, we will use the equation of state and also theorem of the corresponding state. Okay, that one is for the generalized, actually is a generalized correlation. Okay, theorem of the corresponding state is just like Z equal to Z naught plus omega Z prime. There is omega there. Okay, eccentric factor. Okay, so the equation also, some equation they have eccentric factor and some equation don't have a eccentric factor. So you have to know how to differentiate, how to use the equation. Okay, so what is the difference? Okay. Okay, clear. Okay, so this is the equation of state. How to say? Dia punya overall yang you boleh nampak lah untuk equation of state. First, ideal gas equation. Okay, ni yang you pernah guna. Virial equation pun saya rasa dekat mass balance dah pernah guna. Tapi masa bila yang guna virial ni? And then cubic equation is we divided into van der Waals, Radikwan-Soft, Robinson, and also generic equation of vapor-like routes and liquid-like routes. But selalunya saya suka guna yang ni sebenarnya, dua ni. Sebab of course, first before you use this equation, you have to know the phase of the system, whether liquid, gas or liquid and vapor, kan? Ah, okay. So dekat sini bila you guna ni, tapi you kena information daripada sini lah sebenarnya. Kena masuk daripada sini. Okay. And you have to do the iteration. Okay. Iteration. Dia penting iteration dekat sini, iteration penting. Macam mana you nak buat iterations? Okay. Please make sure when you do calculation is converge lah. Okay, the error is become small from the previous value. Okay, faham ya? Kalau tak tahu buat iteration, you kena refer balik buku matematik lah. Ya, apa itu iteration? Okay. So let's see the virial equation of state. Okay. Kalau awak tengok dekat sini, virial equations, okay. Actually from the auxiliary thermodynamic properties, ini just a derivation lah. Okay. Selalunya kalau kita akan ambil virial daripada sini lah. Dia tak akan panjang lah. Ini kalau awak ingat Taylor series kan. Okay. So kita bila you tambah ni dia akan become more accurate, tapi saya rasa kita just sampai sini. Okay. And then we can rearrange this equation lah. Just a derivation. And then you can use lah. Okay. So we can get this one. Okay. For this equation, okay, yang ni kita panggil two terms lah. And then truncated three terms. Okay. So bila tiga ni makin more accurate. So awak kena ingat when we want to use these equations for the calculated, when you want to use these equations, okay, you have to remember that the pressure should be below than 15 bar. Okay, low to moderate. Okay, you boleh guna. Tapi kalau if more up to 50 bar, okay, 15 to 50 bar, okay, below than PC, okay, you kena guna yang 3 truncated. Okay. Sebab dia punya intermolecular interaction tu dia makin ni lah. Makin tinggi repulsion and attraction lah. Okay. Makin visible lah. Okay, makin significant Okay, faham So B ni biasanya value ni kita akan dapat daripada handbook of the engineering, like Paris Chemical Engineering. Okay. I'm not sure in for the new books whether they provided or not the coefficient for B and also C lah. Okay. Tapi selalunya kalau for the test and finals, we gonna provide that the value of B and C lah if you want to use the virial. But we have another equation which is generalized correlation letter. So you just use the table lah. Okay, and the value of B and I think the B naught and B prime is available in the main textbook. So just determine that the value of B naught and B primes. Okay, and then you can use that equation lah. Okay, so that equation generally I would suggest that use that generalized correlation lah later. Okay. Okay. The ideal gas. Okay, kalau you tengok sini ni saya punya kenapa you guna ideal gas kan compared to virials, compared to the high to moderate and also high pressure lah. The term BV arise on account of the interaction between pairs of molecules. Kan, CV is 3D, three body interaction. Okay, so you kena ingat lah why we use virials instead of ideal gas question. Ideal gas interaction assume not existed. Assume you assume that the interaction is not exist, but it's exist actually, but very small, it's not significant. Okay, tapi kalau you consider under microscopic level, dia memang ada. Ya, faham ya? So V increase, the composition of BVC is decrease. Okay, P meaning that approximately close to zero lah, V become infinity. So is approach unity lah. Tu yang saya kata tadi tu lah. Kalau P approach kan Z sama dengan 1 kan. So maksudnya kat kawasan ni lah. Dia just kawasan ni. Okay. Kan. So bila P approach zero, kan? So infinity lah. So Z is equal to 1. Lepas tu Z ni equal to 1. Tapi dia ada range dia lah. Nanti kita akan tengok dia punya figure. Okay? Faham ya? So internal energy as function of pressure. This one is ideal gas. If you still remember equation to calculate the apa internal energy for the adiabatic condition. What else? Work kan? So saya rasa awak masih lagi ingat kot mass energy, I guess lah. Okay. How to calculate the apa ya? Q apa? Heat heat. Itu saya rasa awak masih ingat lah. Okay. So this is for the ideal gas. The relation kita recall balik lah. Okay. Kalau you ingat H equal to U plus PV kan. Okay. CP CV plus R kan kalau nak convert lah. Okay. Heat capacity, constant pressure, CP and CV. Yang ni constant volume kita jarang lah guna constant volume ni. Kalau mikroskopi kita banyak guna constant volume. Okay. Delta H integration of CP kan. Delta U CV kan. This because this is internal energy lah. Okay. And from that one we can expand the equations to calculate the works and also heat kan. Okay, so this is we can apply for the following process: isothermal, isobaric, and as well as isoporic. This one is a constant temperature, constant pressure, and constant entropy. I think isoporic pressure. Okay, isoporic. Constant volume constant volume saya rasa isoporic. Cuba tengok. Saya lupa pula. Saya tentum isoporic ni selalunya saya lupa. Okay. Faham So bar, because bar ni saya tahulah pressure. Thermal ni biasa temperature, korik ni. Okay, constant volume. Yes, constant volume. Sorry. So this is from only for the ideal gas. Okay. So Q equal to negative W, Q to delta H, CP, and also this one is constant volume. Okay, the work is equal to 0 lah because it's constant volume and no work. Okay, and this is the equation that relationship with the CP over CV lah in omega. Okay. Okay. So let's see this one. Can you do this one? 1 mole of ideal gas with CP and CV expand from P1 equal to 8 bar and T1 by each the following path Okay, I think this one we assume as a ideal sebenarnya. Okay. What you have to do, you have to calculate the W, Q, delta U, and delta V for each process constant volume, constant pressure, and also. So you have to refer this one. This one. Can you do the calculation? What is the answer? Can you take a piece of paper? If constant volumes, this one lah. W is equal to 0 lah. Kan? Okay. You have to calculate CV lah. Can you calculate? A constant volume. What is a value of Q as well as delta H? You have to calculate the delta U and delta H, right? Can you calculate? So from this one, if constant volume Q is equal to delta U kan, CV dt. Kan? Betul tak? So dapatkan CV. CV ada ni. R is a R gas constant lah. Okay, R we use 8.314. Joule per mole dot Kelvin. Can you calculate value of Q, and Q is equal to negative U, right? Q equal to delta U. And then delta H. Delta H equal to CP delta T. Sebab ideal gas kan. CP delta T. Okay. Can you calculate? W of course is equal to 0. Right. Okay, you have to find the final temperature T2. Yeah, give you 5 minutes. Give me the answer. Q and also delta H. So since we don't know the final temperature, right? We only know this one. So if you still remember the previous question, right? Okay, we just use this relationship, the ideal gas. V1 equal to R P1 equal to P2 V2 because Z is gonna be same, right? RT2. So you can get the final temperature lah. The volumes is gonna be the same lah because it's constant volume. Right, R is the same. So you can calculate the temperature. Oh, what is the final temperature first? Give me. What? 75 Kelvin. Yes. T2 is 75 Kelvin. So you can determine delta T. So from delta T, you can calculate delta H and also delta U, right? Okay. CVDT. How about other student? I say Malaris ya. I just randomly uh, pick one name. Ni udah belajar kan dekat Maths and Engineering kan? Okay, before we go to Virial as well as what is it? Ni lah, Virial and cubic equation of state. Saya ingatkan hari ni sempat lah. Tapi tak sempat ada masalah tu. Ya, apa jawapan? Azimah? Azimah? Saya lupa pula nak prepare apa tu. Yang daripada Google tu apa. Jamboard. Okay, nanti next class saya prepare Jamboard. Biasa saya suruh Jaring. Azimah. Dapat jawapan Azimah? Azimah ada tak?
Ya, saya doktor.
Dapat.
Masih buat lagi.
Semua dah dekat dalam UTM ke?
Saya belum lagi.
Ha?
Kalau saya belum lagi.
Belum lagi. Oh, dia face by face eh. Tapi dulu pernah masuk UTM tak? Ke tak pernah lagi?
Belum lagi.
Belum lagi?
Ha.
Oh, seronok UTM. Kena masuk. Kalau tak, tak adalah kehidupan universiti. Tapi nanti dah nak masuk dah, endemic dah kan apa. So, it's okay lah. Okay, dapat jawapan. Apa yang ada jawapan tu boleh. Ang Jia Ying, Choi Kah Ying, ni semua ada. Fu Sheng. Siapa yang ada jawapan boleh letak dekat chat box. Saya lupa pula nak ni, provide Jamboard. Nak fee. Okay, ni dah lebih dah 5 minit. Kita dah dapat dah final temperature. So bila you dapat delta T is just T2 minus T1 lah. So you can get what is it, 75 minus 600, right? So it's going to be 500, negative 525 for the delta T. So once you determine the, what is it, T2, okay, from the equation of Q equal to, sorry, I have no, what is it, like a Wacom is what we call it, touchpad. So I use this mouse. So CV dt lah. Okay. Since this is the question, so we can use CV R dt delta t. So just substitute to this equation. So since CV is equal to 5 plus 2 and 5 divided by 2. R is 8.315 joule per mole that Kelvin, and delta is equal to negative 525. Okay, so you can get Q equal to delta U lah. Okay. Similarly, also you apply for the delta H. Okay, constant pressure. Delta H equal to CP R delta T lah. So you can get answer for delta H. Okay, that is for the constant volume. Okay, faham eh? Okay, so the main thing is you referring this equation lah, isothermal, isobaric, and isochoric. Okay, how about the constant temperature? So for the constant temperature is the isothermal. So since there is no change in the temperature, delta U and delta T is going to be 0. And you have to calculate only Q lah. Q is equal to delta W. Okay, just replace this equation with the volume 1 and volume 2. I think we didn't use V1 and V2 since there no information about the V2 and also V1. It's given only P2 and P1, right? So you substitute into this equation. So you can get answer for the isothermal. For adiabatics, okay, adiabatics, what we have to determine is this one lah. Okay, so for the adiabatics is, of course, Q is equal to 0. Okay, because there's no change for the heat. Okay, no release heat or no absorb heat. Q equal to 0, right? Okay, and W is going to be equal to delta U lah, CV delta T. Yeah, this one for the adiabatic process. Okay, so you can calculate. Okay, is it going to be similar with the answer is going to be similar with the for the A? I don't think so, because you have to calculate T2. Okay, the final temperature. Okay, so if you want to calculate the final temperature, you have to use this equations. Okay, TP, this one. Okay, so you can get this relationship, CV and CP. Okay, so meaning that this equation is going to be T2 divided by T1. Okay. And P1, P2 divided by P1. Constants meaning that TP1, TP2, TP1, T1, P1 equal to T2, P2 lah. Sama. Okay. So you kena tengok sini. Okay. And then kat sini mana saya punya cursor ni? Selalu hilang je. Bila guna saya tak guna yang ni wireless kan. Selalu hilang. P2 divided by P1. So you guna relationship lah. This one you can get this one T1 sorry. T1. So you can get T2 lah. So you have to recalculate the final temperature. Yeah. So and then you can calculate work and also what is it? Work and also what you have to calculate delta H and also delta U. Okay. So this is for the ideal gas. Okay, so let's look at the virial equations, how to use this equation. Okay, but mostly we didn't use this kind of the virial equation. Okay, we're gonna use a generalized correlation lah. Okay. Okay, so kalau awak tengok kat sini, tadi dapat jawapan. Berapa final jawapan Q dengan untuk yang constant volume tu? Amira? Amira ke Awira? Amira. Dapat tak? Azimah. Amira pula. Azimah dapat jawapan Azimah?
Dapat.
Berapa?
Q dapat ni. Untuk A kan?
Ya, A je.
Untuk Q saya dapat negatif 10912.125 Joule.
Joule per mole Joule per mole kan? Unit kena ingat Tak ada unit salah tau. Itu awak kena ingat. And then delta H?
H saya dapat negatif 15276.
Tak payahlah panjang sangat. You convert to kilojoule lah. Negative 15.28 kilojoule per mole lah.
Okay.
Itu panjang sangat. At least how many decimal point is 2 or 3 is enough. No need until 5 or 6. Okay. Even if you do the plant designs, just make it into 2 decimal point. Okay, later that one is for your project for the last semester. Okay. If you look at here, that reported values for the virial equation of isopropanol vapor at 200 degrees C are B equal to negative 388 cubic centimeter per mole and C is equal to negative 26,000. Is it cubic? Not cubic ni. Centimeter power of 6 lah. Saya tak tahu nak panggil atau apa. Per mole negative 2. Okay, mole negative 2 lah. Okay, so this is the coefficient for the virial equation is given already. Okay, for the isopropanol vapor at 200 degrees C. So what you have to do is you have to calculate V and Z for the isopropanol at 200 degrees C and 10 bar by the ideal gas equations, and you have to compare with the truncated virial equation of 3 terms. Okay, can you calculate for the ideal gas equation? If you want to calculate by using ideal gas equations, just using PV equal to Z, ZRT. Okay, Z is equal to 1. Okay, so please calculate. And B, okay, truncated virial equations, 3 terms. So if you look at here, okay, virials. Virial. This one you have to use. Yeah. Why we use this truncated virial equation? If you look at here, okay. Yeah, let's explain. I need your opinion okay. It's stated that 200 degrees C and 10 bar. Which equation do you think is more appropriate or more accurate for the calculation of the volume? Okay, is it ideal gas equation or virial equation? And state the reason. Kenapa? Apa? Haris ada, Muhammad Haris. Which one is better for the calculation volume? Haris.
Maybe ideal gas kot.
Kenapa?
Sebab pressure low.
10 bar lu. Ya
Tinggi
betul.
kalau tinggi
10 bar tu macam awak pump basikal tu.
tinggi ni lah kena pakai Varial equation lah.
So look at here is we consider is moderate. Okay, whether you use a 2 term or 3 terms of Varial equations. Okay, but this one is already suggested that the 3 terms, so it's much more accurate lah. Okay, based on the Taylor series pun kalau you question tu lagi panjang, dia akan more to accurate, close to the real value kan. Okay, you have to remember that. What you have to do is you have to know the condition first. Okay, is it high pressure, low temperature, low pressure, or single phase? Okay, liquid or gas? All those things you have to consider lah. Okay, please calculate ideal gas and Varial equation. Okay, once you calculate the ideal gas equation, I think you can get answer. Okay, later just text me through this chat box. Okay, for the truncated Varial equation, kalau you tengok dekat sini kan, the problem is we have V and V2, right? So how can we use this equation? Kan? Dia rearrange balik lah. Okay. So kalau awak tengok kat sini, ini adalah sama dengan ini adalah sama dengan ni kan. Okay. So you substitute this one to this equation. Okay. Faham? Faham? Z kan, this is a Z equal to 1 plus B divided by V plus C divided by V2. So we're going to have a 1 V, 1, 2, 3, 4. 4 Vs. Mana you nak kira volume kan? What we have to do? Siapa boleh suggest? Kita ada 4 V tu. So your equation is PV equal to 3. Any suggestion? Sebelum saya panggil nama? Tak payah takut-takut pun. Salah pun bukan yang apa-apa pun. Kan? PV equal to RT. Apa nak suggest? Apa yang kita perlu buat? This one. Kita ada 4 V ni sebenarnya. Macam mana awak nak dapatkan V real V ni? Apa saya nak panggil? Anyone? Irene Tianxian. Irene, are you there? Macam saya
Yes,
panggil.
Doctor.
We have 4 V's. How can we solve this equation?
I have no idea.
No idea. Okay, dah ambil ni dah. Persamaan terbitan matematik dah ambil kan? Matematik 1, matematik 2 kan? Okay, so what you have to do, if you look at here, alamak, masih hilang je lah saya punya kerja ni. Itu masalah tu. Okay, from that equations, okay, if you rearrange that equation, okay, so you can get so you rearrange this question lah in terms of V. Okay, so if you still remember, you have to do the iteration. I plus 1, this one is Vi, and this one is Vi. Okay, so first iterations, okay, you can guess the value of volume from the ideal gas equation. What is the value for the ideal gas? Anyone can give me the answer for the ideal gas equation? Pusheng, are you calculate? You got the answer for the ideal gas? Okay, Irene, you have the answer for the ideal gas? Irene?
Still calculating.
Still calculated. Oi, kalau macam ni memang tak ni lah. You nak buat iteration lagi ni. Biasanya memang iteration. Okay. So look at here. If we start with the zero lah, V naught lah. Okay, zero. Okay. So your equation is gonna be V. This one is become V1 lah kan, and this one is become V naught. This one is become V0 lah. So meaning that. So starting from the ideal gas equation answer, you substitute lah the volume of V0 here and also V0 here. So you can get for V1. Okay, boleh eh? So V1, once you get new V, you substitute into V1. This one is become V1 and this one become V2 because I is equal to 1. 1 plus 1 equal to and I is equal to 1. So meaning that you can get V2. So you have to do the iteration until the value is converged. What's the meaning of the convergence? Meaning that, okay, the new value is going to have a low error compared to the previous value. Okay, for example, V2 and V1, if the error is like 0.01%, we can consider that is the final answer. Okay, for example, you calculate until V5, V4, and until V5. Okay, so you can get, when you compare V5 and V4, is almost similar, the answer, like 3900, and for V4 and V5 is 3901, right? So the error is very, very small. So you can select that answer lah for your final answer. Okay. So can you do this iteration? How many iteration that you can get? And compare with the ideal gas equation. Irene, you give me the answer for the ideal gas equation. Yeah, I give you 5 minutes. Iteration step, we will deal until the end of this chapter actually. Not only this chapter, but for the other chapter also. Okay, I hope that you can master with the iterations process. Eh? Give me the answer. Faham tak? Ada siapa tak faham tak ni? Faham ke tak faham? Saya punya kerja asyik hilang je. Apa saya tak tahu macam mana kerja saya ni. What is the answer? Okay, if you look at here, the unit is centimeter, cubic centimeter, right? So the R, you just use R is equal to 3.14. Okay. Apa lagi ada lagi tak? Okay. Apa lagi 83.1 per mol per Kelvin. Hilang lagi. Tak nampak. Jadi invisible pula. Bila saya tak gerakkan jadi tak visible. Okay. Okay, Irene. Ideal gas equation. What is the answer?
So sir, is that the answer for B?
What? Yes, what is the answer for A and B? If you have B also, you can give me the
No,
answer.
I mean the volume.
Volume? Yes, I have. What is the answer? But I'm not sure it's correct or not. I have the answer.
393525.
Okay, 3934 cubic centimeter per mole, right, for the ideal gas. Lebih kurang lah tu. Almost lah. How about the virial?
No, you calculate.
No. How about other student? Okay. Apa saya nak bagi? Saya punya kerja ni asyik hilang je bila guna ni. Apa nak panggil lah? Megat Alimi. Macam
Ya, doktor.
pernah masuk kelas saya? Tak ada, tak pernah.
Tak pernah.
Dah ada jawapan Miriam equation.
Kalau yang A tu dapat kot. Tak tahu betul tak.
Tu tadi Irene dah kasih tahu dah. Yang B,
Lepas
B.
tu yang B tu masuk dalam formula three term lah kan.
Ya,
Yang
cerita tapi you kena rearrange lah equation tadi tu. Nampak? VI plus 1.
RT kan. RT over P.
Betul?
Lepas tu kurungan 1 plus BV plus CV square.
Yalah, betul. Yalah.
Lepas tu kalau masuk saya dapat 3539.
Berapa iteration awak buat ni?
5 kot.
35 5 iteration? Ya, kalau V1
tak
awak
ada.
dapat apa?
First iteration kan tu. Salah.
First iteration.
First iteration. Salah.
39. Ini sama je, awak kena buat lagi. Sebab
Kena buat sampai 5 kali ke?
ya, sebab awak punya ideal gas equation, kalau awak tengok, berapa awak masukkan tadi? 3934 kan?
3934 yang first tu.
Kan?
Yang dia gas.
Ideal gas kan yang dimasukkan kan? Tapi
Ah.
V1 awak dapat berapa?
3539.
Kalau awak tengok ni berapa error dia? Cuba awak tengok. Cuba tolak ni, bahagi dengan awak punya nilai asal. 3539 tolak dengan 3934 bahagi dengan 3539. Berapa error dia? Besar ni.
11%.
Besar tu. Besar tu, awak kena buat iteration ni.
Lepas tu kena buat sampai dia berapa persen?
Sampai dia
Sure.
mati lah kot.
Sampai dia mati.
Sampai dia converge lah. Contohnya
Ah.
macam 3, 4 yang contohnya after 4 iteration kan, dengan you compare dengan iteration yang ketiga dengan yang keempat kan, dia kecil sangat kan, macam 0.5% ke 0.1% ke, acceptable lah.
Okey. Maknanya kena buat banyak kali ni.
Ya, betul. Masukkan yang value V1 tadi yang ke dalam equation tu pula as a second value lah, bukan initial value.
Okay. Alright. Thank you, Doktor.
Okay, semua faham macam mana buat iteration? Okay. Rasa okay kot. Okay, awak buat lah. Ni tutorials next week. Tutorial ni saya rasa sama je. Nanti awak buat. Saya mungkin letakkan dalam ni kot. Dalam assignment. Yeah, any questions about the ideal gas and also virial equation? Ada soalan tak? You know the condition, right? Okay, if you want to use low pressure is valid, ideal gas is valid only for low pressure, but once we considering the moderate or high pressure, we have to use virial equation. Okay, whether you want to calculate pressure, volume or temperature lah. So this is in term of the pressure. Okay, ada soalan? Is it clear? Kita masuk cubic equation of state sikit je. Ada soalan tak? Tak ada Okay. Masa tak jalan. Okay, let's see the cubic equation of state. Okay. This is actually part 2 lah. Okay, I will explain about the cubic equation state and also generate cubic lah. Okay, some example and also tutorials. So, kalau you tengok kat sini, mostly cubic equation of state is a part of the equation of state. So we consider as van der Waals, Radicon, soft Radicon. Radicon soft lah, saya suka panggil soft Radicon sebenarnya. SRK. Frank Robinson, PR and also generic. Okay. Generic, we have vapor and liquid. This is important, you know the phase first, whether liquid or solid, because it's different the equation between for vapor and as well as liquid. Okay. Faham Okay, generally, if you look at here, this is a general equation, okay, for the cubic equation of state. Okay, we have a part we call it as a repulsion as well as attraction. Okay. And if you look at here that B, theta, K, lambda and apa ni epsilon is a parameter is dependent on the temperature and also composition. Okay. So this is just a general. But once we convert this one, when we derive this equation, okay, we can get the general equation for the cubic equation of state. Okay. So if you look at here, this is the generic equation cubic equation of state. You have to remember this one. Not remember lah. Sebab dia open book ataupun you nanti kalau you dah kerja pun you guna software juga. Okay. But this is the basic lah. Okay. So all the parameters kalau tengok kat sini. Okay. Sambung ya. Epsilon and so you value in table 3.1 of state is referring whether you want one or all the other punya the parameters. If kilowatts just in the previous slide. Okay, pula. Okay. Kalau buku lama for don't have the new book right now. Oh, I think the buku saya yang baru.
Doktor, macam sangkut-sangkut.
Reduce temperature. Yang alpha TR. Okay, alpha TR substitute with PR. This one, this one, and also this one later for the calculation. Okay, this is important. Table ni is panggil you akan refer table ni. Suara sekarang okey tak? Okey tak? Line ada masalah kot? Sekarang okey? Okey, sekarang dengar. Sekarang dengar. Okey, kalau awak tengok dekat sini, kalau you nak guna equation yang ni kan, nanti dia ada tambah lagi sebenarnya. Value alpha, beta. Sekejap Okay. So table ni, okay, contohnya yang ni adalah biasanya ada alpha, dia guna alpha, ada yang guna A. Okay, sama je lah, alpha TR. Okay, sigma epsilon. You substitute dekat yang equation yang belakang. Okay. Nanti ada equation yang kita perlukan, this one saya tak ingat lah, ohm, and this one saya tak ingat apa simbol nama. NZC lah. So you just guna, kalau you guna Radicon, you tukar je yang ni. Okay, you masuk. Okay, kalau awak tengok South Radicon dengan Peng Robinson dia ada omega dekat sini. Ada omega. Expansion omega. So alpha SRTL awak kena masukkan yang ni. Omega ni you boleh refer dekat table B1. Okay, appendix. Sebab tu saya kata textbook is important. Omega, TC, PC, ZC, TN you kena refer dekat table B1. Okay, dekat appendix. Okay, faham Okay, and the rest is just a value you just substitute to the previous equation or other equation that need these parameters. Okay, sometimes for the accurate calculation we use Radicon-Soft and Peng Robinson. Okay, because there is omega. What is omega? Is the eccentric factor. Later I will show you what is the difference equation between equation that have omega and also don't have the omega. Okay. So this is the parameter for the van der Waals. Okay, once we reduce the equation to the van der Waals equation, once we substitute all the parameters theta kan. Okay, you can get this equation now. Okay, if you want to calculate pressure. And B and also A, if you look at here, right? So you use this equation and substitute by TC and PC lah. Okay, kalau you nak guna yang equation yang ni pun boleh juga. Tak ada masalah, sama je. Okay, so this one is TC, PC and you substitute, you can calculate the pressure. Okay, if you use the van der Waals. Okay, so this one is in the polynomial form in terms of the volume lah. Okay, what you have to do similarly, because this one in terms of volumes, okay, in terms of polynomials, what you have to do actually, if once we already substitute this one, right? So you have to bring to the right side, and you have to do the iteration to calculate the volume, just like you did now with the visual equation, because you look at here that they have a 6V, right? A 6 not 7. Okay, so what's the method that you have to do is just by using the iteration process. Okay, iteration step lah, to get the final volume. But I don't like to use this kind of equation. I like to use the generic equation. Okay, the generic equation, the other one, this one. Okay, this one iteration, you just do the iteration for the Z. Okay, and then you substitute into PV equal to ZRT, and then you can get answer for PVO2. Okay, okay, this one in terms of pressure and also the volume. Okay, faham ya? Okay, so this one is just the how to this one lah. Okay, because I wrote here will be discussed later, right? This is actually is the derivation how to determine this parameter actually. Okay, but for now I think you just use this equation lah. Okay, no need for the derivation lah. Okay, this is just based on the combination of critical point and also van der Waals. Okay, I don't think I'm going to explain this one. Although I have the I actually I prepared the derivation. Okay, tapi dah lama dah saya tak explain in terms of derivation. So yeah, you just use this equation. Okay, faham ya? Okay, so let's see the other equation of state parameter. Yang ni saya skip sebab ini derivation kan. Okay. Okay, ini yang tadi tu derivation. Yang ni nanti skip dah. Yang ni skip je lah. Yang ni skip. Kalau you nak hide slide tu pun you hide je lah. Ini just derivation. Okay. Okay, yang penting yang ni Radicon. Sama juga. It's going to be similar. Okay. In term of P and also volume lah. Okay, polynomial form, right? So kalau you ada software, you boleh solve by cubic equation solver ataupun guna Excel kan. Is okay. Kalau you guna Excel pun tak ada masalah kalau you nak guna ni. Tapi kalau exam tak boleh. Sebab tu saya tak suka guna yang ni. Sebab yang ni kalau you guna manually, you kena bawa ke sini kan. And then you kena buat iteration VI plus 1 lah. Yang ni in term of P lah. Okay, and then just substitute. This one is value of ni panggil apa? Ohm Okay, you just refer to the Radicon. This table. This one. Since you use the Radicon. This one, right? You just substitute to that equation. Faham Okay, Radicon can be a liquid and also gas phase. Okay, especially to calculate the volume. So if you look at here that this one kan, saya convert to VI plus 1. So yang ni special untuk gas lah. Kalau liquid you guna yang ni lah. Okay. Tapi itulah yang saya kata ini memang kalau you guna question ni dia tedious lah. Okay, it's quite tedious. Okay, so dia tak panggil tak panjang lah. Okay, saya lagi suka guna yang nanti generate tu. Okay, faham Okay, and similarly also for the SKR and also Peng Robinson lah. Okay, so this one when you have to convert, you have to substitute this omega. Substitute to this equation alpha. Kan? S ni masuk sini. And this one is substitute to this one. Sama juga. Okay. Yang ni masuk dalam ni. B omega S. Mana? Oh, dalam ni. Sama juga. And then substitute dalam ni. Okay. Sama Faham eh? So ini how to use this equation lah. Okay, I just explain what's the difference between uh, the equation that have omega on omega. So kalau awak tengok teori ni kan, all fields when compared with the same temperature and reduced pressure have approximately the same Z and all deviate from ideal gas behavior to about the same. Ni maksudnya for the Redquang and van der Waals only applicable for argon and krypton and xenon also. Just only these three. Okay, sebab apa dia deviate ni dia tak banyak. Okay, dia tak akan deviate banyak. Okay, kalau ni untuk argon, krypton pun dia akan atas ni juga. Okay, kalau untuk xenon pun dia atas ni juga. Tapi kalau kita deal with the methane, dia akan deviate banyak. Ethane dia akan deviate banyak. Hydrogen dia akan deviate banyak. Okay, so that's why we need the omega. Okay, for the more complex fluid. Faham eh? Okay, faham? Nampak tak ni? Why we use eccentric factor. Kalau awak tengok krypton kat sini kan, tapi yang lain ni dia deviate banyak. Sebab tu we need the eccentric factor. Okay, so we include the eccentric factor, we compare at the reduced temperature and pressure, and also at the eccentric factor is equal to 0, reduced temperature at 0.7 lah. Okay, so kalau awak tengok kat sini, kita compare dekat sini. Okay, reduced temperature and pressure. Okay, sebab kalau tengok ni 1 TR and log P set. The same value of omega. Sebab tu we need the omega. So we can calculate for other component like and octane. Okay, kalau yang ni argon, krypton, and xenon dekat atas ni kan. Okay, sebab dia deviate banyak, so you need the omega. That's why we need to use Penn-Robinson as well as soft Redquang lah. Okay, or other thermodynamic equations. Okay, faham eh? Okay, ada soalan? Generic kita akan next week lah. Saya akan explain next week. Faham eh? Sebab generic ni yang saya selalunya tekankan lah. Yang senang nak faham. Faham eh? Ada soalan? Ya? Kenapa?
Boleh ke aluk e-learning?
Apa dia?
Recording.
Okay. Nanti saya upload.
Sebab I slow sikit lah.
Okay.
Terima kasih.
Okay, tak apa. Nanti next class kita akan ada banyak tutorial sikit lah. Faham eh? Okay. So kalau tak ada soalan,